The invention of the laser has absolutely changed our world. From laser eye surgery to correct eyesight, to robotically assisted surgeries that involve lasers. In the telecommunications industry, the invention of the laser has allowed fiber optic cables to carry and transmit enormous amounts of data, so the entire internet literally runs on laser light. But what exactly is laser light, and how does it differ from regular light? In other words, how exactly does a laser work? The word laser stands for light amplification by the stimulated emission of radiation. Now, in this context, when I say stimulated emission of radiation, I'm talking about radiation being not something that hurts you. Laser light is radiation. All electromagnetic waves are light waves, and they're all considered radiation. So when I say stimulated emission of radiation, I just mean stimulated emission of light. So there's some amplification going on. There's stimulated emission of radiation, which is more light. So what the word is telling you is there is photons stimulating more photons to be created. Light amplification and stimulating more radiation, which is more photons. So what we're going to find in a nutshell is that inside of a laser, there's an amplification process where it's a cascading chain reaction where one photon can trigger additional photons to be released. And then those photons can trigger more photons to be released, and more and more and more, and that's the amplification going on. And then through the process and how it's built, we can focus it into a beam, which we see as a laser. Now, what are the main properties of lasers? We have to talk about this before we can describe how it works. Three main properties. The first one is what we call monochromatic. Monochromatic is a fancy word that means that the laser light that comes out has the same color. And which we mean the same wavelength. This is the symbol lambda, which means the same wavelength. So when things have the same wavelength, they're the same color of light. Notice the light is usually red, but it can also be green and even blue now. And so, but it's always a pure color, monochromatic. Second property is that laser light is what we call coherent. Coherent light means it has that all of the light waves have the same, what we call phase. Now, phase just means that the waves that come out are all lined up, essentially. So here we have a wave, like this, and then we have another, that's a photon, let's call it, and then there's another one that's traveling with it, and I'm just going to draw it kind of right on top because they're lined up. The crest and the troughs are lined up. If there's a third photon here, they're all lined up, they're all lined up, they're all lined up, they're all lined up. If they were shifted with respect to one another, they wouldn't be in phase. All right. Next, we say that it's collimated, which means it's a thin beam. And you all know that laser light has that very thin beam. So we're going to talk about all of that. So these are the properties of a laser. Now we have to dig in a little deeper, and you have to understand that all light that you see, all light comes from atoms where the electrons in the atoms are jiggling around, jumping into higher orbits and falling down into lower orbits. We call them energy levels. All right, so we're going to do a quick little cartoon of an atom, but just know that this is simplified. This is the nucleus where the protons and the neutrons live, and surrounding the nucleus we have these different orbits. Now, it's not really like a solar system, but we do call it orbits because the first models of the atom were thought of as a solar system. But we know now that it's really not quite like this, but we can still use this picture. It's still very instructive. Now, what we say is that there is a lowest orbit that we have. We call that the ground state. And electrons love to live in the ground state. So I'm going to call this an electron, and I'm going to put a little E there, means electron. Now, I'm drawing the electron as a ball, but it's not a ball. Electrons, we now know from quantum theory, they're all waves. But still, I can draw it as a ball so you have something to visualize a little bit better, a little bit easier to visualize. Now, imagine a red-hot poker. You put a poker in the fire. The poker has iron or whatever's in there, steel, and there's electrons surrounding those atoms. The fire is heating up the metal, and the electrons are jumping up into a higher energy state. When I say higher energy state, I literally mean that the electron jumps up into a higher orbit and it temporarily lives in this location. It absorbs energy from the fire and it goes up here. But you see, electrons don't like to stay in the high energy states. They want to be as low as they can in a low energy state. So almost immediately, this electron goes back down into this ground state right here. And during the process of falling in like this, and again, it's not falling in like a planet. That's a quantum thing we'll talk about in more detail later, but you can imagine it doing something like this. But when this process of going to a lower energy state happens, then what happens? A photon is released. So this is a photon released, photon. And a photon is just a packet of light. And light is a packet of electromagnetic waves. Electro, because there's an electric field present in the photon, and magnetic, because there's a magnetic field present. Traveling together, they're a packet of electricity and magnetism we call an electromagnetic wave. We call it a photon. Right? This is called spontaneous emission. If I put the poker in the fire, the electron pops up because the energy of the fire, it absorbs the energy, it goes up here. But when it falls down, it releases the energy and it releases it in a photon. But it's what you call a spontaneous emission. It just happens whenever, and it usually happens very, very, very quickly and rapidly. Right? That's what a glowing poker is. The red color you see is those electrons coming down into a lower energy state. It's analogous to on Earth. This pin is at a higher energy state, and when I get closer to the Earth, it's in a lower energy state. Because if I drop it from here, you see, it can't really hit the ground very hard. So the energy, it's not much energy there, so it's not hitting very hard when it's converted to kinetic energy. But if I drop it from a larger height, it has more potential energy because when it hits the ground, it's going faster. So higher up, things are higher potential energy. That's what I mean when I say higher energy state, like this. Now, what we want to do is harness this. We want to talk a little bit more about this, and we want to harness these photons to make our laser light. That's what we really want to do. So let's zoom in a little bit on the energy level situation here. I'm going to draw the nucleus a little bigger. Remember, the nucleus has protons and neutrons down here. And what we're going to do is, above that, we're going to draw a couple of different energy levels. So we'll say this is the lowest energy level the electron can exist in, and then there's energy level above that. So we can call this as energy level, and this is energy level. All right? And when the electron starts up here and kind of falls in, for lack of a better word, to this state, it had to have lost some energy. Because up here is a high energy state, and here is lower energy. So if it goes from here to here, it must have lost some energy. So where does the energy go? It travels out as a photon. Right? And the energy of this photon is equal, the energy of that photon is equal to the difference in the energy levels here. This is all predicted by quantum theory with equations. You can calculate exactly what the energy of the photon will be. I'll show you in just a second. So this little difference here is called the energy difference, right? Now, in quantum theory, when you get down into the details, you learn that the energy of this photon, E, the energy of it, is equal to hf. Now, E is the energy, and h is what we call Planck's constant. It's just a number, though. It's just a number. And then f here, this is the frequency of the light wave. So if you know the energy of the photon, which we know because of the decay of the electron, we also know its corresponding frequency, which is related to its color. Now you can take this equation and you can substitute in for what the frequency is equal to, and also say that the energy is equal to h, Planck's constant, times the speed of light c divided by the wavelength. So again, the wavelength is this lambda down here. This is called the wavelength. But notice that h and c are just numbers here. So if I know the energy of the photon, I know its wavelength. If I know the energy of the photon, I know its frequency. And wavelength and frequency correspond to the color of the light. So I'm trying to get you to make the connection. If you know the energy of the photon, you know the color of the photon because you know the wavelength and the frequency of the photon. All right? And by the way, when I say wavelength, what do I mean? I literally mean if there's an electromagnetic wave that begins to repeat itself here, the physical distance between here and here in space is a certain number of meters. Now for laser light, it's typically red, although there are other colors, and it's usually somewhere around 650 nanometers. 650 nanometers. Nano means 10 to the minus 9 meters. So very, very, very small fraction of a meter is the length of the wave that comes out of one of these lasers. For red light, okay, it depends on the color, but for a red laser, that's what it would be. All right, so we're getting to where the rubber meets the road. We know how to make matter emit light. We can just heat it up in a fire if we want to, but we want to harness the photons and somehow line them up to make a laser, which is what we're trying to do. So what we want to do is we want to make many of the atoms emit photons all at the same time. So if I have a nucleus of an atom here, and a nucleus, and a nucleus, and a nucleus right here, right, then what I can do is I can draw maybe 2 different energy levels for each of these atoms above, right? And what I can do, if I could figure out a way to pump up and put a bunch of electrons in all of these atoms into the highest energy state right here, then I would have what we call a population inversion, because I would have a bunch of electrons in a higher state. They never want to be in a high state. Everything wants to be as low as it can, just like on Earth, okay? Close to the ground. So this would be a population inversion up here. The problem is, if you only have 2 states like this, as soon as the electron gets up there, within a very small fraction of a nanosecond, this electron wants to go back down to a lower energy state. So they all are going to decay immediately. And what we don't want that, because we want these electrons to all be hanging out in a higher energy state. And we want to get as many of them as possible so that when we trigger it, then they all fall down at the same time, roughly speaking, and then we have a bunch of photons released at once. So the problem is we want the population inversion to last for a long time. So what we have to do is use a material that doesn't just have 2 energy levels like this close together. What we do is we choose a material like this. So here's a nucleus, here's another nucleus, here's another nucleus, here is another nucleus. And what we want to do is we want to pick something with a ground state like here, and then maybe 2 energy levels closer together up here. So here's 2 energy levels for electrons to hang out in. You can think of these energy levels as like parking lots for the electrons. And what you want to do is you want to take electrons from the ground state and you want to pump them up to this higher energy state right here, right? And then what they're going to do is almost immediately they're going to fall to this intermediate state and they're going to start to hang out right here, right? So we have them hanging out here. This is really the magic of what makes lasers work. I could skip it, but then you would lose the whole thing, right? This intermediate state right here, this is very important. This intermediate state, this is called a metastable state. Metastable. It means it's stable, but it's not stable forever. If you can get electrons to all hang out in a metastable state, they're going to stay in there for about 1,000 times longer than they will in one of these other states that I drew in the above diagram. So you have to choose the material carefully. The first lasers were made of ruby, or some of the first lasers were made of ruby, and there is this metastable state in the electron parking lots, energy levels, that has a metastable state. So what we do is we use either light or electricity to pump these electrons up into this top level. They immediately fall down here, but they are able to hang out in this metastable state for a longer period of time. Then what happens is spontaneously, the first one is always going to be spontaneous. Spontaneously, this electron is going to cascade and fall down into this energy level. We know what this energy level is. We can put that into this equation. This is a number. This is a number. This is now we know. And we can calculate the wavelength of the light that's going to come out of there. So a photon is going to come out of there. This is a photon. Now what's going to happen? This photon is going to stimulate one or more of these additional electrons. Stimulated emission, remember? It's going to stimulate it to fall down and release another photon. So what's going to happen is when we get over here, this photon is going to literally collide with this electron and it's going to cause another photon to be released. But the original photon is still there. So I had a random decay causing a photon, but when it hits this, I have the original photon plus a new one that was generated. And then when it hits the next atom, of course, this one, when it goes down here, it releases another photon, but you see there's trillions and trillions of atoms. So from the first photon, I can get 2 photons out from the decay. Those 2 photons hit 2 additional atoms and then create 2 additional for a total of 4. And then it just goes exponential like that. So you get a chain reaction of tons of photons going, essentially a stimulated emission, like a chain reaction going on inside of the laser material, inside of the ruby, for instance. So how do we cause this to make a tight beam, which is what the laser actually is? They grabbed a cylinder of ruby, which is very carefully constructed. Literally, it's ruby cut into the shape of a cylinder. So this is a ruby, and I guess I'll just write here, this is ruby rod. It's literally a rod made of ruby, right? And then on the outside of that, they wind it with a flash tube. Let me kind of try to draw that. It's going to be something like this, right? Something like this. And then over here, you could have a circuit. Now, I've drawn this as a wire, but actually the flash tube here is another tube of glass that has a xenon gas. There are other gases, but often they use xenon, just like a flash bulb from a camera. And what you can do is you can cause that flash bulb to go off and pump a lot of white light, very high energy, into the ruby because it's surrounding the ruby there. That light is going to pump up the electrons into this high energy state. And then they're going to fall into this metastable state, which is the population inversion, and then the laser process can occur. So let's talk a little bit more about the ruby itself. I'll do a side view here. Here is a side view of the ruby, right? Like this. So looking on the side. And then on the top, I'm going to draw the flash bulb. The flash bulb I'm drawing as a rectangle, but really it's a coil that goes all the way around it like this. So this is the bulb. Flash bulb, right? And then down here, this thing is the ruby, right? So what's happening is the flash bulb is flashing and flashing and pumping the electrons up into the population inversion on the inside. When one of them decays, as we said right here, a photon is generated, which triggers another photon, which triggers more and more and more and more, and then you have lots and lots and lots of photons, and all of the photons have the same color. Why? Because all of the electrons, or a vast majority, were in the metastable state. So when they decay, they create photons that are all identical to each other. They're all identical in the same color, and so the same color and the same energy. So what happens is, inside of here, of course, there's atoms. We'll just draw some dots here. There's atoms inside here. And if one of these photons is actually, I should say, on this end, the ruby is polished and it's a mirror. So it's 100% reflected mirror on this end. So anything that hits the inside is going to bounce off. And then over here, it's a 98% reflected mirror. Right? Only 98% though. That means it reflects 98% of the light back this direction. Now, if a photon happens to come from this atom, and hit this mirror at an angle like this, then it's going to come and it's allowed to leave the tube. And so anything that's coming at an angle is just going to exit the ruby rod, and it's going to be lost. Okay? But what we're really trying to do, and what actually does happen, is that when a photon is generated from this atom, some fraction of them are going to go down and hit the mirror at the end. And 98% of them are going to be reflected back the other way. And then they're going to hit this one and they're going to go back this way. And so what you have is a bunch of bouncing back and forth between the ends of these mirrors. This is called an optical cavity, a resonant optical cavity. It's the amplification that's going on because every time the photons travel through all of those atoms with the electrons pumped up into the higher state, they're triggering them to all fall down, generating more photons. But when they generate more photons, again, a fraction of them are bouncing back and forth and causing the process to continue until finally you have so many of these photons all traveling in the same direction, all with the same color, and all with the same wavelength. Remember we said that they have the same phase. So all of these photons have the same crest and troughs there as well. And what happens is, because this mirror is only 98% reflective, and everything is reflected on this side, eventually you're going to get a pencil-thin beam that comes out this way. This is the beam. So the beam that comes out of the end of a laser is actually just the leaking light that comes out of one end because it's only 98% reflective. That is basically how the laser works. Now, one last thing I do want to talk about is that the length of this ruby here is very specially crafted as well. The length of it here, we know the wavelength of these photons. The wavelength is the distance from crest to crest or trough to trough when it begins to repeat. What we do is we create this optical cavity to be, remember this is like 650 nanometers, it's really, really small. So we cause the optical cavity to be a multiple, an integer multiple of 650 nanometers if we're choosing that wavelength for our laser. We choose it to be a fixed length. So the optical cavity can only contain photons of the correct wavelength because the wavelength of the photons have to fit inside of the cavity. If the cavity is the wrong length physically, the photons can't exist in there because when the wave can fit an entire wavelength in there, then you get the amplification process. If it cuts it off, well then it'll decay. So the length of the ruby rod is very important. The mirrors are very important. The alignment on the mirrors are very, very important. And the laser wouldn't work at all if those things were not correct or were not properly calculated. So I've talked about the resonant cavity. I've talked about the length of the resonant cavity. I've talked about the alignment of the mirrors. Now this is for a ruby laser, right? There are other kinds of lasers. The laser pointer is the same process but with a silicon or a germanium lasing material inside. There's also helium neon lasers with a gas tube, similar process. You have a reflection of photons generating more photons. Now that you know how it works, and when you encounter people that say, well, quantum theory or relativity theory have no use, who cares? Then you can tell them, hey, everything you use every day is running on quantum theory because none of this would be possible without knowing the energy levels of the atoms and how to generate photons of the proper energy. Without any of that, lasers could not be possible, and that would affect medical science, communications, and other branches of science and engineering in the modern world. Learn anything at mathandscience.com.